Hi, Dr. Romano. More physics?
Hi, I want to go over a question with you that's probably one of the most challenging questions in all of general physics. We're going to go over a magnetic field type of question, and I'm going to introduce the two dreaded hand rules, known as the right-hand rules. Let's have a look.
Okay.
Consider a straight wire carrying 25 amps of current. A charge of 10 to the minus 5 coulombs moves at 500 meters per second in the direction shown at a distance of 0.15 meters from the wire. So there's the picture. The red is the wire carrying 25 amps, and here's our charge that is moving at 500 meters per second. Notice the charge is 0.15 meters away from the wire. I'm going to find the magnetic field at a location of the charge and its direction. So we want to find, at this point right here, the magnetic field and the direction. Anytime we want to compare distance and magnetic field, the formula is going to be B equals mu 0 I over 2 pi r. This is a constant, so that's going to be 4 pi to the minus 7. We know the current is 25, 2 pi, and the distance from the wire is 0.15 meters. Notice the pi's drop out and the math becomes pretty simple, and we get a magnetic field of 3.33 to the minus 15th Tesla. Now, how would I do the direction? What I'm going to do is get my right hand and I'm going to point my thumb in the direction of the current. Now, we're interested in this point here. So as you can see, it's going out of the page at the top of the wire and it's going into the page at the bottom. So as you can see, this is going out. I curl my fingers, and by the time it goes down, as you can see, we're going in this direction. So it's into the page. Out of the page would just be a circle. Into the page is a circle with an X. So you're going to have to write two answers for this. 3.33 to the minus 5th Teslas into the page. Part B, find the force and its direction on this particle. Well, how do we relate force and magnetic field? The formula would be force equals BVQ sine theta. Well, first of all, if the field is going in and we have the wire going in this direction on the x-axis, that's perpendicular, so we're going to deal with 90. Sine of 90 is 1. So we're going to have the B, which we already calculated, 3.33 to the minus 5. We know the velocity, and we know Q. And the sine of 90 is 1. So we get 8.33 to the minus 7 newtons. All right, hold on to your seats now. What we're going to do is we got to get the direction of the force. What do we have? We have a positive charge, that was the 5.5 to the minus 5th, moving out of velocity into a magnetic field that's going into the page. Now, you got to use another hand rule. So what I did here is I'm going to put it here so it's easier for you to see. I'm going to take my right hand and I'm going to point in the direction of the velocity. Now, this rule is only for positive charges. For negative charges, it's done in the opposite fashion. So what we're going to do is I'm going to take my hand and put it in the direction of the velocity. I'm going to curl my fingers in the direction of the magnetic field. So as you can see, now keep your eye on my thumb. The direction of the magnetic field of my fingers, it's going out of the page. We don't want it out of the page. We're saying it's going into the page. So if you go into the page with the magnetic field, my thumb points upward. And that's going to be the direction of the force. So by the right-hand rule, the second right-hand rule, we come up with a final answer of 8.33 to the minus 7 newtons upward. So therefore, the trajectory would be like this. All right, that's probably about as hard as you're going to get on the exam, on the OAT exam. I have a couple of more examples in the Physics Destroyer using the right-hand rule. So remember, for this problem, there was two right-hand rules. One right-hand rule applied to the current in a wire, and the other was for the force direction related to a magnetic field. All right, this is a tough one, probably the toughest one you're going to see. Hopefully it'll help.
Thank you, Dr. Romano. You made something really tough easy. I really like the way you explained that.
It is tough. Good day to you.
Good day to you, sir. Look at all those flags for the different schools. I want to go to Yale. Good day to you, sir.